So multiple roots. How can we work out whether a polynomial has multiple roots or not? So here's the idea. If a polynomial, we know it has a root at x equals a. So it might be a double root, a triple root, whatever. So we call it multiplicity m, whatever the root is. So double root, multiplicity 2, and so on. So if it has one, then the derivative will also have that same root, but of order 1 less. Now where that's useful is if you've got a cubic and you know it's got a double root, well then differentiate it, you're going to get a quadratic, and that's a lot easier to factorise and work out what the root is. So here's the proof. It's got a multiple root, so therefore I know it can be factorised as x minus a to some power times some other polynomial. If m's greater than 1, otherwise it wouldn't be a multiple root, and x equals a is not a solution to that polynomial I've called qx. If we differentiate it using the product rule, so write down the first, diff the second. Well, I don't know what the derivative of qx is, so I'll just call it q dash x. Plus write down the second, qx, diff the first, but in order to differentiate the first, we're going to have to use our chain rule, anarchy. Bring down the power, m, lower the power, m minus 1, diff the inside, 1. Tidying that up, there is a common factor there of x minus a to the power of m minus 1. Now that's the key bit. So that means a is also a solution to this, to the power of m minus 1. The other thing I have to make sure of is that a is not a solution in the other factor. So that other factor I'm just calling rx, but a is not, because x minus a q dash x. Okay, that bit's going to be 0. But the other bit is plus m times qx. And we specified right at the start there that it was not a solution to qx. So therefore it can't be a solution to the whole thing, because it only works for part of it. And there's our proof. All right, let's use the idea. Going to solve this. They've told us it's got a double root. Well, if it's got a double root, we'll investigate the derivative. 3x squared minus 8x minus 3. Factorises to be 3x plus 1, x minus 3. So that's telling me the double root is either negative 1/3 or positive 3. It's going to be one of those two things. Which one will I logically choose? Well, if I look at the original polynomial, it's monic. So there's probably more chance it's going to be an integer solution rather than a third. So that's probably the one I'm going to choose. So that's not likely, because I know 3x plus 1 is not going to be a factor of that cubic. We now know it's going to factorise to be x minus 3 squared. That's going to be one factor. Well, the other factor's got to be linear, because it's order of 1. And, well, I can just go constant times constant. Negative 3 squared is 9. 9 times what gives me 18? 9 times 2. So solving it, x equals negative 2 or x equals 3. 1991 question. You'll notice it actually comes from an extension 2 paper. Let x equal alpha be a root of this polynomial. And 2 plus b squared can't equal 4a squared. That'll become obvious why we need that as we go through the question. So show that alpha can't be 0, it can't be 1, it can't be negative 1. Well, I'll just use our factor theorem. Polynomial 0 when I sub in is 1. So 0 can't be a solution, because it doesn't work. Let's try that with polynomial 1. Well, I don't know what a and b are. So polynomial 1 is 2a plus b plus 2. I can't be 100% sure whether or not that equals 0 yet. Let's have a look at polynomial negative 1. Minus 2a plus b plus 2. Again, I can't be 100% sure whether that's equal to 0. But that's where the information they gave me is now going to come in handy. 2 plus b squared can't equal 4a squared. So therefore 2 plus b can't equal plus or minus 2a. Which means plus or minus 2a plus b plus 2 can't equal 0. And they're the two expressions that I've just come up with. So I've now proved that neither of those can equal 0. Therefore, polynomial 1 can't equal 0, polynomial negative 1 can't equal 0, so alpha can't be 0, 1, or negative 1. Show that the reciprocal, so 1 on alpha, is also a root. Well, I'll use the factor theorem again. If I substitute in 1 on a, I get 1 on a to the 4 plus a on alpha cubed plus b on alpha squared plus a on alpha plus 1. I'm going to write it like an algebraic fraction and have a look at the top of the fraction. Top of the fraction is polynomial alpha, but we know alpha is a root, so therefore that's 0. Well, if that's 0, 1 on alpha must be a root. So what's that saying about this equation is every time we get one root, we automatically know another one because the reciprocal will be there as well. Interesting. That result will always hold when you have palindromic coefficients. If you actually look at the equation we started with, and just the coefficients, you've got a palindrome there. So anytime you see that, that'll always be true. If alpha is a root, 1 on alpha will also be a root. Same question, but now we're going to deduce that if alpha is a multiple root, then it has to be a double root, and 4b is equal to 8 plus a squared. If alpha is a double root, I just said anytime you've got one root, you know the reciprocal's there as well. So if alpha is there twice, 1 on alpha must be there twice as well. So if alpha is a double root, 1 on alpha must also be a double root. So that accounts for 4 of the solutions. But hang on, we've got a quartic. And we know that a quartic can't have more than 4 solutions. And we've found 4, so there can't be any more. If alpha is a multiple root, then the only possibility is it's going to be a double root. So no roots can have multiplicity more than 2. There's our derivative, because we're still going to prove this 4b is equal to 8 plus a squared. How am I going to do that? Well, I'm going to find the derivative, because now I know it's got multiple roots. They will also be solutions to the derivative. Alpha is going to be a solution, because it's a double root. 1 on alpha is going to be a solution, because it's a double root. There must be a third solution in there, which I don't know what it is. I'll just call it beta. That's going to have 3 solutions. So some of the roots will become 1 plus 1 on alpha plus beta. That's going to be minus 3a on 4. Some of the roots 2 at a time will be 1 plus alpha beta plus beta on alpha. That'll equal half of b. And then product of the roots will end up being just beta is minus a quarter a, because the reciprocals end up multiplying together to give 1. Okay, let's play with this. If I substitute the third one into the first one, I end up with alpha plus 1 on alpha is minus a half a. If I now substitute the third one into the second one, right, I get 1 minus a quarter a alpha minus a quarter a times 1 on alpha is equal to a half b, which I've factorised just a middle bit to get alpha plus 1 on alpha, because over there on the left-hand side, we've shown that that's minus a half a. So if I sub that in, I now have 1 plus an 8th a squared is a half b. Multiply everything by 8. I've got the relationship they wanted me to show. A tangent to a cubic has 2 solutions only. So if you've got a tangent going to a cubic, it touches at one point, but it must cut it at another. So it'll end up having 2 solutions. The tangent, that x value there, will be the double root. So when you solve them simultaneously, you'll come up with a new equation or a new polynomial. The double root will be the point of contact for the tangent. The single root will be where it's cutting the curve. So that's just a little guide. I think we need that in one of those questions there.